Now, let's carry on with Horkheimer's foundational paper of the Frankfurt School, arguably traditional and critical theory. Okay, so on the previous couple of videos, we've got to the point where Horkheimer is trying to motivate this view that theory, in the traditional sense, right, was came to be thought of as kind of this abstract structure of base propositions derived however they were, but they sat at the base. Then they had a derived proposition, so some logic operating on the base propositions got you these other propositions, and those were kind of like predictions. You could go out and check against observation, and hey, then the system's working well. And that model of theory came to be abstracted and seen as sort of the natural, the only way to do theory, right? So an abstract structure, it's actually something that's kind of independent. It's kind of like a Platonic form of knowledge. And that becomes the essence of theory. And that's the only real way to do theory, is like this sort of very thing that's been carved out by the sciences, right? So if you want to know how you really should be doing theory, you do it the way the sciences do it, and they do it like this. So this is a particular view on how sciences work, right? And Horkheimer is trying to challenge not science itself, but the interpretation of how scholars have thought science actually works, right? So this is kind of like a philosophy of science, right? It's you're not challenging necessarily what the scientists say in terms of their actual domain, but what they might say about how they go about it and what kind of results about the nature of science that they have. And Horkheimer is saying that understanding science and is sort of this traditional theory in this way, that's wrong-headed. So in order to motivate that it's wrong-headed, right, we saw that he brings in, well, science, actually theory itself is a historical construction. And then that gets into the problem of, well, is the very content and everything about a theory a historical construction? And I said, like same thing, like arithmetic. Yeah, the whole ball of wax that we call arithmetic, right? All that stuff is historically constructed in the sense that it comes about in history. You learned arithmetic propositions and all this kind. Same thing with geometry. Euclid was a real guy and he was doing his geometry and abstract notions of mathematics, group theory, Galois theory, all that kind of stuff, and plane geometry as well. Those are all historical constructions. But should we then move to say, while the very notion of how they're formalized, that is all historical too. There's nothing left over after the history is emptied out. The very content of 1 + 1 = 2, that's also just a historical product, kind of like a painting, right? Okay, well, Horkheimer is saying, okay, let's have a little bit more of a look at this, right? And he's trying to motivate this a little bit more, that, yeah, in the end, it's got to be tied in with science. Doesn't get to escape and be some sort of window. And think of, like some people say, well, science is the one window into the metaphysical world because we've got mathematics and all this stuff. Horkheimer is saying, calm down. That's not the right way to think of it. Let's look at how theories change in science, right? So that was a big discussion of in the early 20th century about theory change. Why? Because you had the toppling, basically the final toppling of Newtonian mechanics and the ushering in of general relativity. And then atomic theory, the sort of the notion of, the world is fundamentally made up of atoms that are like little billiard balls crashing into each other according to definite rules. And if you know the states that are all here and how everything's moving, oh, well, just some equations, you could bang on those out and say what's going to happen over here. Then you get this weird quantum theory that says, it's not quite like that. There's no real billiard balls. It's kind of energy all the way down. And then it gets even weirder that, well, no, you can't say for sure about everything. Some things are deterministic, but determinism doesn't rule the entire show like it did in classical mechanics. So you got statistics involved. So theory change was a big topic and a major concern amongst a variety of branches of knowledge, right into the roots of science itself, and of course all the philosophers of science. And there was great overlap. Some of the great mathematicians like Henri Poincaré and Hermann Weyl, they were pretty good philosophers too, especially a guy like Poincaré. So Horkheimer is kind of, he's not a lone wolf in this stuff. There's a lot of people talking about this kind of stuff. And theory change is what he goes into here. So I've put a little gamma here about sort of the traditional model and all that. That's what Horkheimer wants to challenge by looking at theory change. So this kind of approach I've labeled with a little alpha. So theory change, he says, really, when you think about it, it can only be understood in concrete situations, right? So theories are not only built up in concrete situations, they change within concrete situations. You cannot think, you can't really understand them. And I think in the end, Horkheimer is making kind of a quasi-Kantian argument. Like, if I can show you that you can't understand any of these things outside of historical conditions, you can make all the claims you want about metaphysical stuff. It's not really intelligible. Even to understand the metaphysical claims, I need historical conditions. So something like that, I think, is going on in Horkheimer. But there's a lot going on in here. Anyway, so theory change can only be understood in concrete situations. So theory is deeply connected to human activity, in terms of its content, right? So what theories are saying about the world, that's deeply connected to human activity. The structure of theory, right, is deeply connected. It's not some abstract structure. No. Remember in the previous video, it's connected to the immediate concerns of a scientist, just like, again, Einstein and the quantum physicists. They were trying to solve real problems when they came up with all that stuff. They didn't just sit and stare at the wall. We like to think of stories of Einstein just staring and thinking and doing all these thought experiments, which he did, but he was also very well versed in the problems of his day. So were guys like Heisenberg and Bohr and Niels Bohr and all that stuff. They weren't just dreamers that they just popped out of nowhere. And Isaac Newton, same thing, when he developed his theories. He was a working scientist, right? He was concerned with real problems and trying to come up with theories to address those real problems. And Horkheimer is saying, yeah, exactly. That's how science works. So theory change, again, is deeply connected in all of its ways. So we really can't understand it in that abstract way, to think of it as this abstract structure. That's just wrong-headed. So if this goes through, then this is really not the correct way to think about theory. Traditional theory, once again, is some kind of mistake. It's a reification. It's something that, that we come from experience, and then we have this abstract thing, and then we project it like out into some sort of real existing kind of Platonic form, right? The Platonic, it's not a thing that we've constructed. We eventually say, oh, the construction is something real, right? That's the reification problem. And that also, you can find that in a lot of philosophers very concerned about reification. It's not just Marx. I mean, somebody who's very different was Alfred North Whitehead, a great British thinker, process thinker, and highly skilled in mathematics. Actually had a theory of relativity that he thought was better than Einstein's, and it wasn't, but he thought it was on the same level. And it was a pretty interesting model of it. But he was very concerned with the notion of reification as well. So concerns over reification, that was big at this time. So that's what Horkheimer is trying to motivate, is this is just all a massive error of reification, and that we've got to bring theory and all that stuff back into the sociological world, back into the world of labor, human production, all that kind of stuff. Okay, so how to motivate this a little bit more, like basically how to motivate this alpha, especially this one about theory change. Well, let's say, for the sake of discussion, you have just a theory. And remember, according to the original model, theory T would contain our base propositions and our derived propositions, right? So you've got those, and then your derived propositions, you're right. Remember, you operate on your base propositions, so a little bit of logic. We haven't addressed the thorny issue of logic, but can't do everything. The derived propositions, and then you're checking them with the experience. Like, oh, do my derived propositions, it predicts this, right? Did I derive my proposition, it predicts something, I go out and check it. Or I have an observation, which I haven't noticed here, and then I go back to my theory. Can my theory account for that? Can I derive, oh, yeah, I see that star looking there. Well, can I do a calculation that confirms that star should be there, or have I got a problem? And if it's like, no, according to the calculations with all this, yeah, that makes sense that star is there according to the theory, so I'm in good shape. Suppose you have an observation, we'll just call it O, and you find out that no matter what you do, with T as is, you can't handle O. And this happens in science, right? Newtonian mechanics had some problem. I mean, it happens, and sometimes the mechanics can handle it. So Newtonian mechanics for a while looked in the 19th century that it was having a little trouble. Some of the planetary orbits weren't, they seem to be having trouble predicting positions of, for instance, Uranus, one of the outer planets. And then all of a sudden it was like, well, you know what? If we use some of the calculations and hypothesize that there's another big planet out there that we don't know about yet, and factor that into regular old Newtonian mechanics, then maybe the weirdness of Uranus, the way we thought was a problem for the theory, maybe with this postulate of another planet, which by the way turned out to be Neptune, we could be able to make a prediction. And maybe if we point our telescopes where the theory says to point your telescope, you'll find a planet there. And they did. So sometimes an anomaly or a problem for a theory can be handled by certain kinds of projections and little tiny modifications, or non-theoretical modifications, like we won't change Newtonian mechanics. We'll just postulate that there's another big planet out there, and that's mucking up stuff. Because we haven't included it in our calculations. Once we include it in our regular off-the-rack Newtonian calculations, I am simplifying a bit here, then all of a sudden the calculations for Uranus's orbit will look fine, and now we've got to find this big planet, though, because if we don't, then the theory's in real trouble. And so everybody breathes a sigh of relief when it's like, yeah, they found it, and it was predicted, and so the calculations were done, and the theory was all cheery. And so it's maintained. But later on, the orbit of Mercury ran into some problems. It gets a little more complicated with this. But put it this way, as the planets go around, they go around in ellipses. Remember studying that in grade school? Not circles, little ellipses. Well, the little point where, because they swing in and they zip around, they slow down a little bit. And as they swing in and zip around, that point that's really close, the closest point of the ellipse, kind of like the little egg shape, when it's closest to the sun, that little point actually moves. So it kind of looks like those old spirograph things, if you could do it. It doesn't just go around on the exact same orbit. The orbit kind of processes a little bit. So the perihelion, the close part, it kind of moves a little bit. And Newtonian science doesn't have a way to account for that, right? So people are like, why is, and it's more noticeable, well, at that time it was the most noticeable was with Mercury's orbit. So all the astronomers are like, what's going on here? The problem of Mercury's perihelion precession, right? So people are saying, hey, maybe it's just like the Neptune problem. There's another planet out there, maybe right around Mercury, and I think it was called Vulcan or something. Yeah, Vulcan. And so they postulated, couldn't find it, until eventually they started tinkering with the theory, and then when they modified Newtonian's theory from big N for Newton to N star for Newtonian modified, the theory had problems with other things that regular Newtonian theory didn't have. So it was getting to be a mess, and then we all know the story. Eventually, ta-da, Einstein comes along, fully aware of all these problems, and starts a new way of thinking about planetary orbits based on a new way of thinking of gravity, not as a force, but bending of this weird thing he called space-time that people are like, what is that? So he cooks up this whole new thing, and it works, and it's amazing. And, Einstein's like, oh, when I figured these equations out, Mercury's orbit just fell out, and it looked great. So, again, I'm being a little bit facetious here, but that was an example of theory change. So what's the moral of all this blathering that I'm doing is when you find you have something, an observation, that doesn't fit the BPs, doesn't fit the derived propositions, it's a mess, you could modify, right? And in a variety of ways, you could introduce like the postulate of another planet, like with Newton, whether it was Neptune or Vulcan, maybe it'll work. Or you can modify, with the case of Vulcan, where you started modifying the actual theory itself. So to go from modify it, so you go from T to, let's say, T star, such that T star now handles the anomaly, right? The funny observation. And let's say you run into problems, but then you modify the theory again. So in other words, Horkheimer is saying you could just rinse and repeat. Repeat, repeat. I'm never going to give a theory up. And Quine talks about this, a great philosopher, Quine. He says, I could just keep modifying my theory. So the minute you come up with something that doesn't fit my theory, I'm going to imply something like, well, maybe all of us had something in our coffee this morning that we shouldn't have had. This is a mass delusion. I can modify a theory like crazy. And we all know people do this, right? It's like when people want to preserve their beliefs, right? People can have, a human mind is amazing at preserving its beliefs that it likes, especially ones that it's attached with, right? That's the whole idea of when people have real problems, when they can't face real evidence. I mean, these are all very abstract kinds of notions, but they're very concrete in terms of our lives. So this is coming up at this level of theory protection, right? I could protect my theory if I'm just allowed to fiddle in any which way I want. I could do that. Now, normally people don't do that. Why not? Because the social situation just becomes too crushing to preserve. I could for a while get away with trying to argue that I'm Napoleon, and maybe some people might indulge it a little bit, but eventually the social pressures are going to destroy that notion. Okay, same thing. Scientists they do it for a little bit, right? They might be, these Newtonian diehards might have kept fiddling and fiddling and fiddling, but eventually they gave up. And Horkheimer's going, yeah, that's what happens. In ordinary experience, we do that. We hang on to things for a while, and then it's too much. I got to give this up. I was just wrong. Okay, finally I get it. So they don't just go from T to T star to T double star to T star, 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 and so on and so on. They do it a little bit, but the pressures eventually, they stop doing it. New theories sometimes win. Why? Because of social circumstances, right? So real social circumstances. Now, admittedly, Horkheimer's not entirely clear about this, but there's just more evidence, more things come about, and new theories, they come in. They logically, in the abstract, I think his main point is they don't have to. You could keep fumbling away. In other words, and he uses this example, and we'll look at more in the next video, but I'm going to end on this point here. He says something like, look, and in 1 century, like if you look in about the 16th century, Copernicanism is hardly mentioned. It's around, but it's hardly mentioned. And then in the 17th century, it's all about Copernicus. Okay, so what's going on here? Well, the earlier theory was the Ptolemaic, was the Earth-centered or geocentric. Copernicus, he wasn't the first to propose. I mean, Aristarchus and a lot of people, a lot of the ancient Greeks, they were already thinking that perhaps the sun is at the center. But according to most scientists and all that, they were running with a Ptolemaic model, which was the Earth-centered. And charts and astronomers' charts for navigation at sea, they worked, and they were geocentrically based. Copernicus comes along, introduces a more theoretical approach with the sun-centered heliocentric model, but he had circles, planets move in circles. That was a problem because remember, they move in ellipses. So the Copernican system wasn't all that much easier than the Ptolemaic. So you could seriously be a scientist and very rational and be like, I don't know if I want to go with this Copernicus thing. It's not like he just published his work and everyone went, yeah, you're right. So remember, we want to think of the history of science in a little more realistic manner, that things had to build up and all kinds of social circumstances changed, and that it sort of like scientific theories don't just go over like that. They're rocked back and forth until the forces just go, and then finally they topple, right? They don't just go over like that. So the Ptolemaic model, it eventually topples. The Copernican model comes in, and Horkheimer then goes on to talk about, look, this stuff, this theory change is deeply embedded. Theory construction is deeply embedded in society and labor, and it's a part of all the general project of a society, the general output of labor. Yeah, it's artistic things, scientific things, changes in art movements, those are deeply embedded in cultures, changes in science and theory, that's also deeply embedded. You know, a lot of this was connected to commerce and all kinds of things. It wasn't just an abstract enterprise, because if it were, you could do this, right? You could play this game if you wanted. They don't. Okay, so on the big pictures of science, they're like the little pictures that we have of the world where we change our views. And then on page 196, Horkheimer says something along these lines, and this is a quotation. The scholar and his science, okay, after going through all this, the scholar and his science are incorporated into the apparatus of society. So they're not outside, they're not sort of doing this thing in the abstract. The scholar and his science are incorporated into the apparatus of functioning of society. His achievements are a factor in the conservation and continuous renewal of the existing state of affairs, no matter what fine names he gives to what he does. So, whatever scientists are saying about what they're doing, right? Horkheimer is saying, I'm taking exception to that. What you're doing and what you're proposing and all that has to be looked at in the context. You are part of the apparatus of society, and these achievements have to be understood as embedded in society, and they have effects and sociological effects, and society also influences science as well. It doesn't get to escape. That's the traditionalist isolationist notion of theory, with all of its abstractions, could be said to hide the links that theory has with the conditions of society. Quote, the real social function of science, then, is not made manifest. Remember when I said you go back and read a general relativity book, you don't see anything about society in there. And it'd be very easy to think that this stuff just fell out of the heavens into somebody's mind. And you know, oh, Newton just fell out of the heavens into his mind, and then Einstein fell out of the heavens, and then everything else, the social change, all that just takes place in the abstract. No, that's the wrong way. Traditional theory then only says what it means in the isolated sphere of science. And this isolated sphere of science itself is a product of social conditions. So, you know, when you think of the scientists, again, I think as Horkheimer is trying to argue that even being able to think of this as a plausible way, that is a social construction as well. So all of this stuff comes about through social conditions. And again, this sphere of this isolationism in science, where it thinks of itself as escaping and thinks of itself in this absolutist independence way, this is all grounded on the social conditions and historically grounded. All right. So then again, as he's trying to argue that it is a matter of fact that the life of society is a result of all the work done in the various sections of production, and science is just another one of those sections of production. Okay, so again, so he's trying to get us to think about science too as, you know, some kind of mode of production of knowledge that is historical, is contingent as well, and it doesn't escape. Okay, well, very interesting. Let's have a look at more of this, because he's just getting going. See you next video.